Hello, thank you for watching this video. My name is Carmen and I'm a graduate student at Caltech. I'm going to present today the work that I did with Dimiter Hall and Jose Maria Maestre on distributed linear quadratic regulator robust to communication dropouts. I want to start by pointing out that this presentation wouldn't be possible without the internet or the power network. These two are very big networks that we need to control, and they're susceptible to unexpected events such as communication dropouts. So one of the questions we can ask is, can we reliably control these networks? And so when I talk about controlling a network, I refer to a system as the one represented in the picture, where each subsystem is controlled by a subcontroller, and all of them work cooperatively to produce the desired outcome, and therefore they need to communicate to each other. They do this in a localized manner, so they only talk to their neighbors and not to all the controllers in the network. So they need to share information in order to work cooperatively, but what happens if for some reason this communication link drops and the controller cannot send a message to its neighbor? How can we make networks robust to this? So this is the formalization of the problem I just described, where we have a structured linear system where the dynamics of each of the subsystems is described below with a bracketed I notation, and each of the subcontrollers of the plant has an internal state. And the way the controller policy, and in particular the communication policy, works is each subcontroller computes a message based on the history of its own internal state and the measurement that it did. They exchange messages with their neighbors, and so this message they are used to update their internal state, and finally they compute the control action based on their own measurement and the history of the internal states. So this what this really means is that the control policy is only done based on local information, and in particular this is reflected by the set of controllers that share messages with subsystem I. So this only models localized information. Now, in the setting that we are considering, not only information is localized, but also the set of subcontrollers that we can communicate to varies with time, is something that we cannot control, and it follows a stochastic distribution. So in particular, this is what happens when a link drops. The set of systems that we can exchange a message with changes. So this is the formal description of the problem that I just described, where we're trying to solve an LQR cost in expectation, because the distribution of dropouts is stochastic with a probability mass function f, and we're subject to linear dynamics and all of the constraints for the controller that I just described, which essentially mean the controller is subject to a localized communication. So how can we solve this problem? This is a tricky problem because the localized communication constraints, what they require is that we restrict the variables on which some variables can depend, and this is a tricky constraint to impose as expressed in this problem. So one of the things that we can do is use the system level synthesis framework. It's specifically useful for tackling that kind of constraint, and in particular the way it works is when we have a linear system as the one represented in the left, instead of computing a controller k, we can go ahead and parameterize the system responses phi x and phi u between w and x and w and u respectively, and those maps represent the closed loop behavior of the linear system. This phi x and phi u is a parameterization of the state and the input. It's linear on the disturbance, and that's what the SLS framework works with. How can we make sure that two maps phi x and phi u represent the closed loop behavior of the system that we originally had? Well, that's the SLS theorem guarantees that. In particular, if phi x and phi u maps lie in the affine subspace that I represented below, then we guarantee that those two maps are a closed loop response of the system, Moreover, if we know the closed loop response of the system, we can compute the controller. Now, not only we can compute the controller, but also we can implement it in a really transparent manner, which is also amenable for distribution. In particular, it can be implemented in the way that is drawn in the slide, and in that way, the maps phi(x) and phi(u) directly show up. Not only that, but because these maps phi(x) and phi(u) parameterize the system responses, we can go ahead and rewrite optimal control problems in terms of these variables. What this means is that we can impose constraints on the synthesis problems, so in the optimal control problems, and those constraints, or in particular their structure that we impose, is directly imposed on the implementation of the controller, just because phi(x) and phi(u) show up there. So that was the main ideas of SLS. And now there is a little extension that we are going to use in this work that addresses the issue: what happens if the problem that we try to solve is rendered unfeasible? Well, in that case, there is some tweak that can be done to it, and is that phi(x) and phi(u), the phi(x) and phi(u) that we try to synthesize, are no longer the system responses of the system, but they're very close to it, and they're very close by a factor of delta. This is what this theorem essentially is telling us. And we know that the controller that results from solving phi(x) and phi(u) and implementing those that are not system responses is stabilizing if and only if this I plus delta inverse is stable. Now, instead of imposing that condition, we can impose another condition that is convex and is a sufficient condition for guaranteeing stability. There is that the norm of delta is smaller than 1. And so the synthesis problem that we'll be solving results essentially in what's written down the bottom. And lastly, in order to go a little deeper into the implementation of the controller, well, I just said that the implementation of the controller in terms of phi(x) and phi(u) was not only very transparent, but also amenable for distribution, and this is what this slide is trying to convey. So in particular, the phi(x) that we've been describing, and it's the same for the phi(u), it's a block diagonal operator where each of the phis inside are matrices. And so those matrices can be written in this block form, where the bracketed notation represent what subsystem is interacting with which other subsystem. So essentially, we could implement subcontrollers that only depend on the neighbors instead of the entire network. And that is what we were trying to convey in the equations for the controller implementation. So we had this problem originally for the problem statement, and now this is the problem that we're trying to solve. It's the exact same problem, only that now it is written with SLS variables, so the cost has been modified to fit the SLS parameterization. The dynamics have been replaced by the conditions from the SLS theorem, and now the most important part of this is that the locality constraints are now affine constraints, making solving this problem much easier than solving a problem subject to the previous constraint where we were restricting dependencies. For reference, this is a robust SLS problem, and so you can see how it matches the structure of a robust SLS problem. So now the only thing we've done is we've modified the original problem that we had set up to match the SLS framework. So essentially we made a change of variables, but we have a few problems still. One of them is that the objective function is not convex in delta, which is one of the decision variables. The other one is that this problem is not amenable for distribution techniques. So we need to, ideally, we would distribute this optimization so its subcontroller solves its own synthesis. Otherwise, since this is applied to large networks, there would be a huge computational overhead. So we're trying to solve these problems. The first thing we do is we introduce a relaxation. So in the lemma, we've proven that the original objective function that we had can be relaxed because it's always smaller or equal than this other 2-to-1 norm by a factor of the magnitude of the delta and the dimension of the operators. So in particular, we could relax the objective function that we originally had and substitute it by the 2-to-1 norm that we just introduced. And this is how the problem would be modified. Highlighted in yellow are the modifications that this lemma introduces. Furthermore, we can go ahead and nail down what this 2-to-1 norm is. Turns out that it is computed on a column-based manner, so it's taking the maximum of the Frobenius norm of each of the columns of phi. So we could use that, take the epigraph of the optimization, and end up writing the following optimization, which is quasi-distributed because all the phis can be distributed in a column-wise manner, and the only thing that remains centralized are the lambda and the c, which are both scalars. So the hope is that this can be solved in a relatively fast manner. We can also show that this leads to a stable controller, and that is satisfied as long as each of the columns satisfy that their one norm is smaller than lambda. Then we know that subcontroller is going to be stable. So if all of the columns satisfy that condition, then the entire network is going to be stable in closed loop. And so just to tell you how we apply all of those findings to design strategies against dropouts, here's one. And that one is, well, if you know that two of your communication links can drop out, then let's design a controller that is robust to those dropouts. So we're essentially picking the worst case scenario, and we implement the phi-x and phi-u that correspond to that scenario. So all of these computations can be done offline. A more interesting one is, well, let's pick all the possible combinations of dropouts that can occur. Even though this seems a combinatorial explosion, that is not the case, because since remember that each subcontroller was only communicating locally to its neighbors, then the number of links is going to remain small even though the network is really big. So we're going to get away without a combinatorial explosion. And so the way this works, we design a controller that is robust to each of the dropout scenarios, and we can do this offline. When we go online, what we first do is we sense what dropout has occurred. We assume that we can do this immediately, and then we implement the corresponding phi-x and phi-u that we had designed for that scenario. Notice that this can be done completely distributed because we had guaranteed stability for each of the columns independently. So we can combine all of these patches of different dropout scenarios for each of the subsystems, and the result would still be stable. So because this is computed in a distributed manner, the computational overhead would be small. And just to show some simulation experiments, we take this chain of subsystems and we play around with the communication links, and we introduce random dropouts. This plant is also subject to Gaussian noise. And so this is what happens, for example, for subsystem 4. On the bottom, you can see the pattern of communication dropouts. The y-axis is representing the set of neighbors that it has an active communication link to. And so you can see how this changes over time. And you can see the performance both for its state and controller in the offline scheme and in the online scheme. You can see how the online scheme, the performance is slightly better, but there's not an overwhelming difference. And in particular, if we compute the moving average for different noise patterns, in particular, each of the lines is computed for 10 different noises, Gaussian noises, and each of the lines corresponds to a different dropout scenario. You can see how the moving average for the online scheme is a little smaller than the one for the offline scheme, but the difference is not dramatic. So you can see how there is a trade-off between the cost and synthesizing all of the controllers for possible dropouts and performance between the two schemes proposed. So as a conclusion, we formulated the problem into the SLS framework because it provides a very comfortable way of synthesizing controllers for networks where we're imposing localized communication. And once we had it in SLS framework, we added a couple of lemmas in order to make the computation convex and amenable for distribution. And once we had that, we were able to propose two different schemes for communication dropout. One of them was an offline synthesis and an offline implementation, so essentially a worst case scenario. And the other one was an offline synthesis of many different cases and an online implementation that senses what case has occurred and implements the corresponding controller in a distributed manner. The future applications for this work are the extension to the nonlinear SLS, applications to MPC, on application to coalitional control. Thank you so much for listening.